For nearly a century, cosmology has relied on a single framework, the Standard Model. It is a set of equations that has successfully predicted the behavior of the universe from the first fraction of a second after the Big Bang to the present day. This style represents a number called the Hubble constant. It measures the specific rate at which the universe is expanding right now. That single figure dictates the age, the size, and the ultimate fate of reality. Astronomers have argued over this number since Edwin Hubble first calculated it in the 1920s, a disagreement so fierce it split the field in half. This timeline illustrates the core of the modern crisis. Imagine trying to calculate the speed of a car on a road trip using two different methods. Method A predicts the speed based on the starting engine specs. Method B calculates the speed by physically measuring the passing mile markers. If you execute both methods correctly, they should match. But Method A predicts exactly 67 miles per hour, while Method B measures exactly 73 miles per hour. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% is enormous. Because a faster expansion rate means the universe reached its current scale in less time, this discrepancy makes the entire cosmos over 1 billion years younger than the Standard Model allows. If both perfectly executed measurements are correct, then the rules we use to understand the history of our universe are no longer sufficient. Method A looks backward. The Planck satellite spent years mapping the cosmic microwave background, the faint afterglow of radiation left over from when the universe was only 380,000 years old. Physicists extract the conditions of that ancient early universe, plug them into the Standard Model, and run the tape forward 14 billion years to predict how fast space should be expanding today. The math produces a highly confident number, about 6 to 7 kilometers per second per megaparsec. A megaparsec is about 3.2 million light-years. So for every 3.2 million light-years you look outward, galaxies are receding 67 kilometers per second faster. Method B ignores the past. A team led by Nobel laureate Adam Rees measures the present-day universe directly. They use a tool called the Cosmic Distance Ladder. By tracking the rhythmic pulse of specific stars called Cepheid variables and comparing that to the peak brightness of exploding supernovae, they step outward to calculate exact distances to nearby galaxies. Rees's team got 73. Two impeccable methods, yielding two incompatible versions of reality. For a while, the easiest explanation was measurement error. Scientists assumed that cosmic dust was blending starlight together in dense regions, making things appear brighter and skewing the measurements upward. Then the James Webb Space Telescope turned on. Its infrared sensitivity was specifically designed to cut through cosmic dust and eliminate visual interference. Astronomers assumed Webb would correct the blending, pull the rogue 73 back down to 67, and resolve the tension. Webb looked at the exact same stars, and the distances held. Its cameras confirmed Hubble's original measurements almost exactly, and the expansion rate stayed locked at 73. With measurement error ruled out by the most advanced technology humanity has ever built, the crisis is undeniable. The numbers are right, which means our underlying map of reality is missing a vital ingredient. The Hubble constant is only the first fracture. Almost immediately, the Webb telescope began finding other anomalies that defy existing equations. It captured images of galaxies in the early universe, nicknamed little red dots, that are far too massive, having assembled themselves much faster than the Standard Model allows. There is also a quieter discrepancy, known as the S8 tension. Direct observations reveal that the distribution of matter across space is noticeably less clumpy than the equations predict. An unexplainable expansion rate, massive early galaxies, and abnormally smooth cosmic structure. These separate anomalies suggest that our cosmological model is facing structural challenges. To fix the math, physicists are currently investigating a hypothesis called early dark energy. This graph maps cosmic expansion over time. If a sharp upward kick of extra expansion occurred in the first few 100,000 years, an era we have never directly observed, it would shift the math just enough to align the 67 and the 73. While early dark energy remains unproven, a new generation of telescopes is actively being built to hunt for exactly these types of hidden forces. You might expect a crisis to spark panic, but the prevailing mood is one of productive anxiety. There is a sense that we have pushed our current understanding to its limit, finding contradictions that our old models simply cannot resolve. Reaching the boundary of our current knowledge suggests a reality far stranger and more complex than our current math could ever imagine. The next version of our cosmic map will have to account for these impossible numbers. When the James Webb Space Telescope opened its mirrors to the early universe, astronomers expected pristine images. What they got instead was flawless data that actively contradicts our mathematical understanding of reality. For nearly a century, cosmology has relied on a single elegant framework known as the Standard Model. It is a set of equations that successfully describes everything from the first fraction of a second after the Big Bang to the formation of modern galaxies. There were always minor discrepancies in the data, tiny observational quirks that physicists assumed better telescopes would eventually iron out. But Webb didn't resolve the math. Its ultra-precise measurements took a theoretical tension and turned it into an undeniable field-splitting crisis. We have built the most sophisticated piece of observational technology in human history, and its sharpest insight is that our foundational blueprint for the universe is missing something massive. The trouble centers entirely around one specific metric, the Hubble constant. It is the exact rate at which the universe is expanding right now, today. Pinning down this single number has driven a century of astronomical rivalry. One way to find it is to look deep into the past. Scientists used the European Space Agency's Planck satellite to map the cosmic microwave background, the faint radiation left over from when the universe was just 380,000 years old. This chart tracks the timeline of the universe. By taking those early conditions and running them forward through the Standard Model's equations, physicists generated a steady predictive line. It tells us the universe should be expanding today at roughly 67 kilometers per second per megaparsec. But you can also measure the expansion directly. Nobel laureate Adam Rees and his team look at the present-day universe, calculating distances to nearby pulsating stars and exploding supernovae. Their direct measurement clocked the expansion at 73. Look at what happens when we plot that direct measurement. We have an 8 to 9% gap between the two methods. In physics, an 8% error shifts the assumed age of the universe, alters the calculated distances between galaxy clusters, and rewrites the timeline for when the first heavy elements were forged. For years, the scientific community assumed the higher number was a mistake. The reigning theory was stellar crowding, the idea that older telescope lenses, like Hubble's, were accidentally blending the light of densely packed stars together. Blended stars look artificially brighter, which skews the distance calculations. The James Webb Space Telescope, equipped with highly sensitive infrared cameras, was designed to cut right through that cosmic dust. The expectation was that Webb would untangle the blended starlight, correct the math, and safely lower the expansion rate back to 67. Webb stared at the exact same stars. The blending wasn't there. The distances held firm. Webb confirmed Hubble's higher rate almost perfectly, proving that measurement error was a myth. To complicate things, astronomer Wendy Friedman leads an independent team that bypasses those pulsating stars entirely, measuring older red giants instead. Her recent Webb analysis produced a frustrating result of 70, sitting right in the middle. Rees argues her team used a small, potentially biased sample of supernovas, sparking a fierce debate over whose methodology is right. Two brilliant teams are looking at the exact same sky and arriving at different conclusions. It strongly suggests the cosmic distance ladder, the foundational tool we rely on to map the nearby universe, has unresolved structural flaws that a single telescope cannot fix. While astronomers battled over the present-day expansion, Webb pivoted to the deep past. Looking back to the cosmic dawn, just 500 million years after the Big Bang, the telescope uncovered a completely separate crisis. It found little red dots, early galaxies that were impossibly massive. According to the Standard Model, early galaxies should be small and dim, yet Webb detected structures rivaling the Milky Way, assembling themselves billions of years faster than the math allows. Physicists felt a wave of relief when they realized the telescope was being tricked. Many of these galaxies housed supermassive black holes, rapidly devouring gas. From billions of light years away, extreme heat from a hungry black hole looks almost identical to the light of 10 times its mass in stars. But the relief was temporary. Even after researchers mathematically stripped away the blinding light of those black hole imposters, roughly twice as many massive galaxies remained in the data than our physical models allow. The earliest matter in the universe was organizing itself entirely too fast. Webb discovered a massive spiral galaxy, nicknamed the Big Wheel, that existed within the first 2 billion years of the universe. Spiral structure takes time to develop, yet here was a remarkably mature system, sitting inside a young era that should have been defined by chaotic mergers and clumpy adolescent galaxies. Around that same era, researchers found another unpredicted pattern: swarms of young galaxies that were strikingly elongated, stretched out across space like cosmic cigars. This simulation highlights the mechanical problem. On the left, our current model relies on cold dark matter, which builds rigid, clumpy scaffolding. It physically struggles to form smooth, stretched shapes. But on the right, if dark matter behaves more like a fluid wave, it easily allows matter to flow into those elongated streams. Cold dark matter is the scaffolding that determines where galaxies form and how they cluster. If these dark matter particles behave differently than we've assumed, the ripples would propagate through the mass of galaxy clusters and the distribution of dwarf galaxies, changing the very foundation of our cosmic map. If the structural timeline of the past is bent and the expansion rate of the present is broken, what hidden, invisible ingredients do we have to alter to fix the math? One radical alternative is early dark energy, a hypothetical massive burst of extra expansion that occurred right after the Big Bang and then vanished. That invisible kick would adjust the conditions of the early universe just enough to solve the Hubble tension today. Another alternative is wave dark matter. By replacing rigid clumps with a smooth, fluid material, this model explains the stretched, cigar-shaped galaxies while also resolving a secondary tension: the fact that matter appears less clumpy than the standard model predicts. If a single adjustment to our models, like a fluid dark matter or a burst of early energy, can account for both the faster expansion and these impossible early structures, then the Hubble tension and the Big Wheel are likely not isolated errors. They are two distinct cracks branching out from the same underlying flaw in our physics. This systemic breakdown isn't a failure of science. It is exactly what happens when a field reaches the absolute boundary of what it knows and forces its way outward. A new generation of instruments is already moving to meet this problem. The European Space Agency's Euclid mission is currently mapping the geometry of the dark universe, while NASA's Nancy Grace Roman telescope is being built to conduct massive wide-field surveys specifically targeting dark energy. We are a species on a tiny rock orbiting an unremarkable star, using mirrors and math to argue the exact rate reality is expanding. The universe isn't broken. Our map is simply incomplete, and the next version of that map, whatever the data forces us to draw, will be stranger and more magnificent than anything we have imagined so far.